follows on from last week. So let's just kind of look back at this example that we did. So the theory says that if you've got a second order differential linear equation with what we can consider an external force, sorry, my apologies, then the solution is a homogeneous solution plus particular. Now the homogeneous solution is first you solve it equals 0. Okay, how do you solve the homogeneous? Well, you look at you take the coefficients 1, 2, 1 here, the multiple of the second derivative, first derivative and function, and you make what's called an auxiliary equation, this thing with the lambda. You find the roots of that, and depending on the nature of the roots, so you can have real distinct, real repeated, or complex. There's 3 different forms of the homogeneous solution. Okay, then you come to finding a particular solution. So this thing here, this differential equation, has infinitely many solutions, but the infinity is captured in the homogeneous. It's captured in this this A and B. So there's infinitely many ways that you can have an A and a B there, so that gives you your infinite solutions there. So the particular then is just any solution at all of this. So there's infinitely many solutions, you just need to find one of them. So what you do is you try and pick something that looks like the external force. Now how you do that is you use this table. Now it's nice for you, like it's an open book, you don't have to learn this off, you can just use this. And what you have is, if you look at the one here, the sine 2 theta, it's a wave. So you should try something that looks like a wave, and you should have the same angular frequency. So the 2 theta should be 2 theta, but you'll need a cos and a sine for things that we spoke about the last day. So we try this purple thing, and we try and force that into the differential equation, the blue thing up the top. And if we get that, we find that it works if c is minus 3 over 25 and d is minus 4 over 25. So we add the homogeneous solution to the particular solution, and that's what's called the general solution. Now we can get into problems, that the problems I normally wouldn't put on an exam, but for you it's probably likely I will, because it's open book. If the trial solution suggested by the table does not work, so the table can fail, and there's one particular way it can fail. If this happens, if the trial solution is already a solution of the homogeneous system. So for example, look at y double dashed plus y dashed equal to 5. So if you look at the auxiliary equation, the coefficients of the second derivative is 1, the first derivative is 1, and there's no y of t term, so it's 0, such as r squared plus r, and that has solutions 0 and minus 1. So they're real distinct. So you end up with, let me just explain where you just have a. So you should have a e to the minus 0t plus b, actually why am I doing minus 0? That was stupid. E to the minus t. Now 0t is equal to 0, e to the 0 is 1, and a by 1 is just a. So that's where that a on its own is coming from. Okay, now look at the 5. So that's a constant. So the table says you should pick something that looks like 5, that looks like a constant. But if you try a constant, it's not going to work, because the constant is already in the homogeneous. And the homogeneous is something that you put into the differential equation, the left-hand side, and you get out 0. So with a constant, you can't get out 5, you can only get out 0 because it's already an homogeneous thing. So what we could do is write something maybe up the top of the next page. The trial solution, the trial cannot be in the homogeneous solution, because the homogeneous solution is always going to give you 0. So you end up, it doesn't work. So to get around this, you do the same trick as with the repeated roots. Now we'll just remind you. So if you look at this and suppose you get the AR squared plus BR. This is the auxiliary equation. I appreciate this is harder, but than what you've seen before. All I'll tell you is that this chapter is only worth 15%, but the next chapter is harder and is worth 35. You're going to have to work a lot. I'm going to be looking for, you'll have to be submitting work regular. So if the solutions of this as r equal to alpha repeated, this is not, so this will not work. So if you do e to the minus, actually I want this to be minus alpha, no, alpha. E to the alpha t is a solution. If the other solution was different, say e to the beta t, you'd be done, but here they're the same, e to the alpha t, and then you say, oh, I'm multiplying by constants. And is that all the solutions? This fails because you don't have two different solutions. You get the same solution twice. Let me just fix this a little bit. So this does not work. Because this is actually just one solution, because a plus b, it's actually only really one solution. So you need two different ones. So how you got around it is you multiplied the second one by a t. So the correct one is e to the alpha t, fine, multiplied by a constant, fine. The second e to the alpha t multiplied by a constant, it is a solution, but you're not getting all of them. What you have to do is multiply this by t. And we have to do the same thing here. If the trial solution is already in the homogeneous, try a second trial solution where you change the original trial. Say this is the first trial, multiply it by x, or t is appropriate. So you change, see the way you change this by multiplying it by t, you'll change this by multiplying by x, or maybe t, it depends on the equation. So if your trial cannot work because it's an homogeneous solution, you change it by multiplying it by t. So this idea also works in picking your particular solution. In the example above, once we realize that the constant is already a solution of the homogeneous, we should change it by multiplying it by t. Now if we do that, it works because the first derivative of ct is c, the second derivative is 0, so if you force them in, second derivative plus first derivative, where is this coming from? This differential equation here that I have near with the 5, this yoke. So you want the second derivative plus the first derivative to give you 5. You get 0 plus c, which is just c, to be equal to 5, and that works. So the general solution, then you'll add the homogeneous, which we had in the previous page, plus the particular 5t. It turns out that if you multiply by t, you might still have something in the homogeneous solution. I think that'll happen with repeated roots. Well, then you just multiply by t again and do it with t squared. Okay, so that's something that's pretty likely to happen on assignment 2. Not guaranteed. I might go a bit soft on you, but I don't think so. Not with an open book. Okay. So what I got here? So find the general solution of this. So we must find the solution and then a particular solution and then add them together. So first, the associated homogeneous system, so that's this thing, is the second derivative plus function is equal to 0. The coefficients here of the second derivative is 1, and so I get 1r squared plus the there's no first derivative, so it's 0r, and then there's 1y, so plus 1 equal to 0. Now there's a few different approaches for solving r squared plus 1 equal to 0. I'm going to need the space down the bottom. I'm just a bit worried about that. Okay. So what am I going to do? Okay, so I'm going to do two approaches. So okay, say if it just comes to you. Okay, so I'll do the very, very easiest. So look at this equation. There's just r and 1. You can just solve it directly. There's no need for factorizing. Although I like factorizing, you need it for, yeah, maybe we should try and factor first. So if we do the AC method, we multiply 1 by 1 and we get 1. And the only factor of 1 is 1 and 1. And you can't make up the middle term, which is 0, with that, because you'd have to do plus 1 minus 1, but they multiply to give you minus 1 rather than plus 1. So you can't factorize it using that method. So what you do in this chapter is you would use the minus b formula. And sure, we'll go with that. So r is equal to minus b. Now there's no b term, so it's just 0. Plus or minus square root b squared, which is still 0. Minus 4 by a is 1 and c is also 1. All over 2. Okay, so that's minus 0 is nothing. Well, I'm going to keep it there. I actually need to keep it there. 0 plus or minus. So this is square root of minus 4 over 2. And you should know at this stage square root of a negative is I times the same square root. So 0 plus or minus I times the same square root, but obviously made positive. And then this is 0 plus or minus root 4 is 2. So it's I by 2, which is 2I over 2. Now you might be wondering, why do I keep the 0? But that will become clear soon. So 0 divided by 2 is 0 plus or minus 2I divided by 2 is 1I. Okay. Now the alternative is to just kind of solve directly. So if you take away, I'll do it up here, r squared plus 1 equals 0. So I take away the 1 from both sides. R squared is equal to minus 1. Now you have to be careful, there's two solutions here. I'm going to do a square root, which is a little dodgy anyway, but there are two solutions. So if I do a square root and I say I get r equal to the square root of minus 1, I have to realize that with a square there's two solutions, is plus or minus. And now what is square root of minus 1? Well, you could say I times root 1, or else you could just say I at this stage. Well, I'll go slowly. I times root 1, and root 1 is I. Now the question is, if you now want to write down the homogeneous solution, we have to go back. This is even something I used to put on the exams. So this is the form. If it's P plus or minus IQ, this is the solution form underdamped. So the problem is you might be stuck. How is plus or minus I, P plus or minus IQ? And that maybe is where students might get a bit 0 plus or mightn't see it. It's possibly a bit easier over here. Well, in any case, we have our homogeneous solution. The homogeneous solution is, so if you go back and look at that formula from, I think it was page 69, I'll just go to it there, 69. So the P, the real bit goes here, e to the pt, and then the Q is like the angular frequency for the cos and the sine, and then the cos and the sine get multiplied by A's. Right, let's pay 75. So we said that e to the pt, so e to the, here the p is 0, then times a cos, then the q here is the 1, is the multiple of I, so that's 1t, plus b sine 1t. Okay, and now what we can do is we can say e to the 0t. Well, 0t is 0 and e to the 0 is 1, so multiplying by 1 makes no difference. And of course the 1t's are just t's, so we have this a cos t plus b sine t. Now this is beyond underdamped. This, because there's no term with the first derivative, is actually just not damped at all. So this is an undamped spring, not under un. Okay, so that's the homogeneous solution. Now what about the the particular? So we're looking at this. Now luckily nothing like that is already in the homogeneous, so we're going to have no difficulties like what we spoke about at the start. So now the problem of finding the particular solution. So we want something that looks like 3e to the minus t. So 3e to the minus t looks like, and you can look in the table, a constant times e to the minus t. Now what you'll see in the table is the multiple of t doesn't have to change there. And like it's hard, I mean, like how do you know, like if it's t squared, or say it's a t is the external force, then you change to a multiple t. Here you don't, and maybe you can consult the table. Okay, so, and what was the differential equation? It was the second derivative plus the function was 3e to the minus t. So this is going to be our trial solution, and we're going to try and force it to solve this thing here. So we need to find the first and the second derivative. So maybe we've space to find the first and second derivative here. So the first derivative, the trial solution, so we should fix the constant c, and the derivative e to the minus t, we might just go up and make a little note up here. What you have in the tables is that the derivative of e to the ax is a times e to the ax, and so the derivative of e to the minus t, the t is multiplied by minus 1, so you essentially get minus 1 times e to the minus t. I could put little ones in there if I want, and then minus 1 times anything is just minus that thing, and 1 by t is that. So the derivative of e to the minus t is minus e to the minus t. So what I get here is, this is minus e to the minus t. And then I can find the second derivative. So now the constant is minus c, fix that. And I need to differentiate e to the minus t again. And of course I get the same thing, minus e to the minus t. And then the minus c by the minus 1 will give me plus c e to the minus t. Yeah, I'm a little bit worried about this. No, I needn't be. So like you could be worried if, like say if the, so like the y here, the trial solution and the second derivative are equal. So like if this thing was negative, then this couldn't work because I'd keep getting 0. But if that was minus 1, then an e to the minus t would be in the homogeneous solution, and I'd have to change from c e to the minus t, I'd have to multiply it by t. But anyway, that doesn't happen here, happy days. So we're looking at the second derivative of the trial solution plus the trial solution. What does that equal? Second derivative is c e to the minus t. Trial solution is c e to the minus t, and we want this to equal 3 e to the minus t. I'm going to put a little exclamation mark on the equal, saying that we really want these to be equal. We can't be guaranteed that they're equal from the discussions at the start of this lecture, but we want them to be. So we end up with c e to the minus t plus c e to the minus t. There's two of them, so 2c e to the minus t. We want this to equal 3e to the minus t. And just like before, you compare coefficients. If you could get this 2c to equal 3, you'd be done. So you want 2c to equal 3, and you want to get c on its own. How do you get rid of that? Multiplied by 2, you divide both sides here by 2. So you get 2c divided by 2 gives you c. 3 divided by 2 is 3 over 2. So that means that if c is equal to 3 over 2, you have a particular solution. So this is a particular solution. We write it as this. And now we have the general solution is the homogeneous solution, which is on the previous page, a cos t plus b sine t plus the particular, which is 3 over 2 e to the minus t. And the question is, what happens in the long run as time gets big? Now this remains as a wave. It's not multiplied by anything, but this thing goes to 0. And so it's because the external force, the 3 to the minus t, is getting smaller and smaller and smaller. So imagine a spring where someone is kind of pushing it, but with a force that gets smaller and smaller and smaller. Eventually what's going to happen is just basically it's just going to be just the spring oscillating. What would be interesting, and you can see from here, it's basically impossible. But there's probably a certain values of a and b that make it actually equal 0, go to 0. So there's probably a solution where a and b, that's an interesting problem. I might just look at it from for a second. So is it possible that A and B equal to 0? Because then what you'd have is, it's surely possible. Yeah, it's just a question of what would be the initial conditions. I'm going to find that out. I think it's interesting. Actually, didn't need much thinking about. If the initial value of the, if the initial displacement is 3/2, say 1.5. So if the initial displacement, where am I going with x? Y of 0 is equal to 1.5, and the initial speed is minus 1.5. So looking something like that, you get this weird thing. So the force, the external force, is pushing this way. So imagine this is the spring. So the spring is kind of, this is the equilibrium. Okay, now the external force is pushing, it's kind of pushing the spring out, stretching it in one direction, more or less. And yeah, and then what happens is that, of course, because there is an extension, there is a restoring force, the force of the spring. But what's happening is the external force is tuned in such a way that, so it's coming down, it's coming down, it's coming down. When the spring is reaching equilibrium, now if the spring reaches equilibrium, at that point there's no force. But what this external force is doing, it's tuned exactly in such a way that the when it's slowing it down, so that when it hits equilibrium, it basically has no velocity. And so it's like the spring, it's not quite, it is like a damping, but it's a different type of damping. It's done in a totally different way. It's actually quite interesting. And I wonder, like, are real dampers possibly more like this? The only issue is if there's different values of, like, it's not guaranteed to work. Like if it's any bit out, like say if the initial displacement is 2, then it won't happen. You will get oscillations, because what will happen is the spring will be, basically when the external force goes to 0, when it goes to 0, it's not going to be near equilibrium, or it's not going to have no velocity, and you're going to end up with the spring just moving on its own, which isn't damping. So it's like, it's just a few small situations where it does actually have the effect of a damper, but most of the time not. Okay, so that's actually a good segue into the next section, where we're going to find the A and the B.